Okay, thank you, Adrien. Thank you, Abbeal, for receiving me. And hello, everyone. So I'm Valentin, and I will talk to you today about simplicity, about complexity, and about the practical solution we can put in place to software. So a little bit about myself and about Ledger. So I'm an engineering team lead at Ledger. I lead one team in the backend of Ledger. We are doing principally Scala services, financial services, using a lot of Postgres. It's like the team of SQL wizards. If you know this type of team, you may have in some companies. And I work at Ledger. Ledger is a French startup. Now it's a unicorn, and we are doing hardware wallets, which are convenient solution to secure digital assets, basically, so cryptocurrencies, but not only it, passwords and so on. And you can sign message, do a lot of stuff. It's a very nice company because we have like a full vertical implementation of the solution. So from the hardware to the backend systems, to the firmware, to the front end. Yeah. So today we'll talk about complexity and simplicity, which is the completely opposite things, and we'll see how to build large-scale systems. So most of my talk will make a lot of references to a paper published in 2006, which is called Out of the Tar Pit, which I strongly encourage you all to read because it's absolutely awesome, and which is dealing more in details with what I will just go around today. So since the beginning of software, software has bugs. So obviously at the start it was real bugs, just jamming relays in like electromechanical computers. Here you can see the very first mention of a bug in a computer context, which is a report from the hardware. I think it's a Harvard Mark II computer, so it's 1946, and the guy has just scotched the pasted the bug within within the pages, and it's quite funny to see. But obviously, we have more and more bugs. The bigger the software grows, and today we'll see how to not repeat things. So each time you have a system, it's easy to fix bugs after bugs, but it's much more difficult to see how to prevent them. What is the root cause of it, and I won't go over all the quotes. There will be a lot of quotes. I love quotes in this presentation. But this is a very fundamental paper, which is about Prolog, and we'll heard about Prolog later in this presentation. So first, I will put in place some notions about complexity. Mainly where do we find it, what's a bit the taxonomy of it, what are the type of complexity, and how we can analyze it. So first, a very nice distinction to do is to differentiate between essential and accidental complexity. So basically, essential complexity is a problem you want to solve. It's a core business logic. It's very well defined. You have specification of normally what your software is going to do. And accidental complexity is all the things that come around it for in the broader sense, put it into production, to have the software working. For instance, if you want to make a payment from Alice to Bob, obviously the essential complexity is to transfer the fund safely from Alice to Bob, and the accidental complexity is what come over, like programming language, databases, mainly consistency issue and so on. And in this talk, we focus on accidental complexity, so the context around business subject. And to understand complexity, we have two main tools, and we'll get over these tools to analyze the cases of bugs and complexity we have. And the first one is testing, which is quite common now in software development. thanks to the unit testing movement and to the quest to have 100% coverage, which is not exactly the goal we need to reach, but it's a good good goal to have, because you have the system, you want to test a part of the system, you can make cases, runs that the cases are expected, and so on. There is a lot of limitation to testing, and the first one is quite known for a long time out of time. I will use a quote from Dijkstra. So everyone knows Dijkstra from like graph algorithm, and it's like one of the big guy in the computer science history. I told that like testing is useless because no, Dijkstra is a bit of a troll. Okay, testing is useless for him because you can only test the bugs you had and not the bugs you don't have yet. So so we need to find more. We need to find more than testing. Testing is a good requirement. Testing is okay. Testing is nice to have, but testing is not enough. For instance, we need more informal reasoning. We need more static analysis using types if your language has types and so on. And while building this kind of abstraction, we can have more deep knowledge about what our code is going to do and what is really the essence of the problem we try to solve. And really, we will focus on this aspect in this presentation also. So you won't get a lot of slides about testing. That's okay. I don't neglect it. It's just that we'll focus on the other side. Okay, so let's dive into the real stuff. We'll analyze 2 and 3 main causes of complexity in systems in general, and later in the presentation we'll see how to avoid part of this, because I want to be realistic. Not everything is not software. No software is going to be perfect. There will still be bugs, but at least we'll see some solutions soon. Not make a lot of it. So for causes of complexity, the first one and the biggest one you may have heard of is state. So how many people has ever been told by the tech customer support or by just a random guy, I don't know, oh, just restart it and it will work for anything from your phone to your computer to production server databases. Sometimes the solution is just restart it and it will work better, because actually computers have a lot amount of, like a very big amount of state, and this state grows like, it's not even exponential, it's like, factorial is a bit, there is a combinatory explosion of the possible state in a computer. And as said Brooks in this very nice paper, which is the guy who coined the essential and accidental complexity term, actually, you can see that computers are very complex machines, and when you write software on it, it's even more complicated, and it's very difficult to see what are the possible state of a system, basically. That's why testing is working very well when you have very small, isolated unit testing. Works very well because you can enumerate all the cases you want to solve. But actually, when your software grows and when you want to test bigger parts of your system, we can see the limitation. Like, we need to initialize things in real order. There is some like some precedence to have while initializing systems and so on. The second thing we'll discuss about in terms of complexity is this one. It's a very not well-known one, so we'll take a bit of time to explain it. It's control. Basically, when you are writing a program, you are writing letters in some orders. You are writing words. You are writing statements. And by writing statements in most programming languages, you over-specify an ordering on things. For instance, if you take this small computation, so it's I don't know if I can have a mouse. Okay. And by the way, if you want to raise your hand and ask a question, it's okay to do it in the middle of presentation, and don't hesitate. So if you can see my my mouse. I don't know if you can see, but let's see. There was very simple computation. You have A, which is equal to B to B plus C, D, E plus F, and G, A plus D. So obviously G is dependent on the two previous computations. But there you can see that you have this semicolon. And if you use semicolon in your programming language, or if you use just jump a line in Python or in Scala or anything, you are introducing control. You are introducing like a control structure, which is just, hey, do this thing before this thing. And this can be small, but if imagine you have a network, like you have database accesses or network calls between the two, and it can make a lot of difference by interleaving two statements. Obviously, some compilers, when your language compiled, are going to optimize these kind of things. And in this case, normally any half-decent compiler will just inline the calls, not to have to provide like a data structure for A and D. But they're only smart to some extent, and we cannot rely fully on compilers doing work for us because they are not perfect. So let's take this expression and let's write it a bit differently. So we'll take the equal sign and use like a assign function, and like the semicolon, and use the, which is kind of hidden by the semicolon, and then function. Then you can have this kind of code. It might be a little bit alien, but we'll see the point just after. Here you can see explicitly what are like the dependency between assign and then and so on. Actually, in the functional programming languages, you work a lot with this kind of structures because the way program normally functional programming is handling control is to chain function calls. So you can see here the explicit call structure that will be run by the computer. But if you use only semicolon, maybe the compiler will not be able to transform this kind of thing in this kind of thing. Here, I introduced two new things, which is parallel on phone. You can think of it as async await in JS. And this is kind of the ideal thing we want to do. Like, there is no relationship between the first computation and the second computation. They are only needed once we want to compute the third. So actually, by overspecifying an order, we are hammering the performances of our code, and it will be more complex to achieve the most efficient design. And that's why what we call control. Obviously, in like imperative language, you have if, then, else, and so on, which are also used to manipulate control, but at least it's explicit. This kind of thing is very, very tricky, and it's not really easy to spot on the first sight. So anyway, one key takeaway of this thing is like, do things explicitly as much as you can. Okay, so a third funny one. There is a lot of debate on is there less code? If you have less code, does it have less bugs? Experimental results tends to say yes, but let's have a small experiment to see it. Okay, so I will talk about Prolog. So not to enter in too much detail, Prolog is like a solver, a programming language and a solver. So when you have Prolog expression, you can use what is called predicates. Here happen is a predicate. You can fill in predicates with some variables, and you can leave variables not initialized. And the Prolog interpreter is going to try to find what is the missing variable. So here you can see there is a relationship between 1, 2, 3, 4, 5, 6. You call append on it, and it's return you the list. And actually, the compiler, the Prolog interpreter, is able to output the list. But one funny thing with Prolog is like you can also leave other things, not only the last one. Like if you don't know, like if this with this append predicate, you can also find the prefix by leaving. Putting the full list in third position and leaving the suffix here, and as well as the suffix here. So next question, what happens if I leave the two first predicates, the two first variables unknown? And Prolog will happily tell me all the possible combination of prefix and suffix. What I want to show you is like with this simple like append innocent function or predicate, depending on your programming language type. We have like 4 core functionalities, which is I can append to list, we can find a prefix, find a suffix, and find all the prefix and suffix combination to do a full list. And in your mind, how much line of product code you need to program this? And the answer, by using, actually, Prolog is like a database, so you can inspect code that run on it. It's only 3 lines. And okay, it's not obvious, and you need to, I won't get into all the details. It's only 3 lines of very simple Prolog code, and I won't explain all of it, but it's quite, there's no advanced features. Compare this to what you need to do. I attempted to do the same in Python with only the 2 first cases, and it's already like 10 times the length. What I want to make a point is like if you have a programming language or a DSL or a library which has a nice IPA, which is perfectly fitting the domain you want to map, just go for it. Like Prolog is made to find unknown things. So obviously when you have complex like relationships between things, it's very nice to use because you only have to describe relationship between things. You only have to describe what you want to solve instead of describing how you want to solve it. And obviously there is much more bug causes here than here because there is a much higher mental overhead to parse this than this. So we can debate about it later, but that's the point I wanted to make. I took the whole 2 extreme things, like a very imperative language and a very logical declarative language, but you can apply this to even in one programming language. That if I can write a function by still being clear, not doing code golf, right? If I can have a shorter function, which is maybe a bit less performant, but it's not critical code, go for it, even though it's not like what is the most optimized path. What are the solutions to this kind of issues? So the 3 issues we had are like control, state, and code length. And the 3, I will go over 3 solutions programmer has found over the years, which are object-oriented programming, functional programming, declarative programming, and they are not tribes. And one message I wanted to go through, to pass through this presentation is like you can combine all the 3 in all the programming language you want. And it's just different solution to different problems. In object-oriented programming, the main focus is state, and you need to, for handle state, you need to make objects that can encapsulate things, abstract things away, and have a clear API between objects. That's why that at the core essence of object-oriented programming, normally there is something called message passing, which is not really what object OOP program use today. But the core thing is like you transmit message between objects and you don't care about what the object is doing. You only have specification and you go for it. Obviously, you still have some state issues, not that much because at least you encapsulated states that belong together in smaller modules. But you still have state issues, and for control, it's usually there is no like strong resolution of this issue. It's still managed in the imperative way, and so on. And that's why we'll see that later, like functional programming and object-oriented programming emerged like in the same decade, but later people are all about functional programming. The hype is still a bit continuing today. It's a hype, so but it's kind of justified. I'm doing Scala, so I'm based on this, but at least you don't have that much state issue using functional programming because you're not supposed to have side effect in your function, or you need to like put the side effect outside of your business logic and make a clear difference between the two. and that make a lot of sense once you will get. I have one like example later in the presentation. We'll see, and hopefully we can solve a bit of the state issue using functional programming by explicitly telling the function what are its real arguments, like what are the and what are the real effects of your system. For control, it's a bit more complicated because functional programming doesn't seem to have control, but actually, when you evaluate arguments of a function, they are evaluated from left to right. So you imply an order on the thing. That's what the whole point of the control example I gave previously is like when you write things as functions without semicolon, you still have evaluation order, but at least you have some nicer data structure you can have with. And then you will see a bit of the ideal case, which is declarative programming, because you don't have to manage state at all, since you just say what is the state you want to reach, and you have no intermediary state to specify. And for control, normally declarative languages break this evaluation order we've seen in functional programming, because they are like free to evaluate expression in the order they want before they are needed for the results. And actually, the prologue what I presented just before is not a pure declarative programming language, because we still have an implied order in the predicates. But it's a nice try, at least. If you stick to the very functional part of prologue, it's okay. But once you start to do side effects, obviously everything shatters away. So we'll see. Like, declarative programming is the solution to have less bugs, and that's a practical case we have in your code base. Actually, and the more declarative we are, the less bugs we have historically. So I will go over a bit of advices we've collected within years. So first of all is like use configuration as much as you can, because configuration are not subject, they are just that pure data structure. They are not subject to a lot of interpretation and variation, and it forces you to specify things before the program is run. And putting configuration into code can have nice properties, but it makes the program much more brittle, because now if you want to specify different things, you have to do a code changes, do a release, and so on and so on. And if you can have like your code as an interpreter of what this configuration is getting to you, it's a very good state to be in. Second one is API design. So here I don't talk about REST API, but more about application programming interface, like libraries and interfaces you want to put in your code. Be more declarative and let the client declare what he wants. And I have some example just on this point on like collection libraries. So some languages don't have collection libraries which are very like declarative. For instance, if you take Go, I don't know if you know Go, but it's quite easy to read. So the goal here is to find what this function is doing. And actually, it's not obvious from the get-go, because here, what we try to do is to have a map of stop words. You have a line, lines which are a list of string, and we want to filter the token. So tokenized lines, filter the tokens by excluding stop words, sort the results, and take the top 5. So it's the 5 list, like the 5 smallest words in the line which are not in the stop words. Actually, it's very like it's not quite obvious to read. I don't want to trail, but here is the same function in Scala using the collection standard library. So it's much smaller. So we've seen that it may produce less bugs. There is less low-level shenanigans like we've seen with the just use a map string of struct because it's how sets are done in Go, and it's much more readable. So you split rows, you filter what is not containing in the not containing the stop words. You sort by size of each word, and then you take the top 5. So this is again, it's a caricature between two completely opposite take on one problem. Go wants to be as explicit as possible without any magic, and Scala wants to really state like this kind of flat map, filter node, and so on are combinators which are useful to describe the intent of the user, of the programmer. For instance, if you take the Go code, it's very not obvious that this one is this. Oh, I cannot select things. Sorry. This for loop is tokenizing things. This for loop is it's filtering what is not in the stop word. At least you have to read this, and the less you read, the faster you can get. And in my mind, it's pure troll actually. This thing can be generated by ChatGPT, and indeed it was with small modification from my side. This thing did not need to be generated by ChatGPT. Okay. Next point is about state and how we thread state. So we've seen there is a big issue in the state handling in the programming language, which are there are leaking side effects everywhere. If you take this small class, so it's Scala code, but I think it's quite readable. If you don't have an issue understanding part of the code, don't hesitate to ask a question. So you have this mutable contour here, which are a mutable variable here, which is called I. When you increment the contour, you just do I equal I plus 1. So when you want to use it, use the contour. You want to increment it 2 times and get the result. So you create your contour, you increment it 2 times, you get the result. So, but actually, imagine there is another thread using the contour. Then you have to put explicit synchronization into this part of code because there is maybe side effect in this part and so on. And if you want to get back in time, imagine you increment it 2 times, and then you want to get back in time and increment it later on another topic, on another subject, because you had an if branch, and I know there is many cases of this thing. Then you have state to manage. You have to do a decrement function. You have to roll back the state to the previous situation, and that's a situation which is tricky to handle. In this case, it's obvious because it's just a counter. Imagine you have database transaction with several save points, or I don't know, network calls, or remote services that you need to undo or uncommit transaction and so on. And it can grow arbitrarily complex and just within this counter interface here. I didn't put the interface section, but it should be mutable counter here. Let's see how we can put it more manageable using this very nice trick, which is do an immutable counter. So to do an immutable counter, it's not the right title, but then you have a class which contains one counter. Case class, just to see, it's an analogous of data class. So it's a pure data carrier, actually. And you have this increment, and increment is not giving you units, like this is void in most programming language. Increment is giving you a new counter, which is incremented. So very easy. We are doing more garbage, but garbage collectors are very efficient these days. And now the state can be threaded and shared, even in multi-processing environment, because there is no modification of the inner state. You only have new reference of a counter. So to use the counter, we get the counter in argument, and we return it, because if you want to chain operation using the counter, you need to have the new state. And then you can see that we create a new counter at 0, we increment it 2 times, and then we explicitly return it in the last statement. And then other process can take this counter and use it and so on. And what we can see is it's very much more testable and much more really able to use this kind of counter, because you can see, hey, let's have a counter at I don't know 1 to 3, and then input it into the system and see how it goes. Whereas here you have to explicitly set up with a loop and increment it here right amount of time and so on. Okay, and the last point I wanted to go over is like to make invalid state unrepresentable. So in a lot of time, we don't specify enough things about the code we have, and it can lead to very tricky situations, like having wrong data in databases. And let's take databases as an example. Here is a small schema in SQL. So you have to you are like creating two tables, teams and employees, and an employee has a team. He has salary, he joined at some point, he has birthday, and so on. The thing is, like, the schema is complete garbage, because you can input everything. You have to first, you have to sanitize everything in application code, and you can still input garbage into the database, like negative salary. You can delete the team, and it doesn't delete the employees. You can input null first name and last name. Imagine a program called null will like break the database. And actually, I can join a company before I'm born. What we can do is taking this schema and putting constraints, and actually databases usually have a lot of constraints built in, and by using this kind of schema, and it's not like it does costing a lot to type not null if a field doesn't need to be null. But it can make a lot of difference in expecting really hard production bugs. And for instance, first the last name are not null here. We check that the date are in the right order. We check salary is positive, and this is very basic, like SQL, DDL. Normally, PostgreSQL has it, SQL has it. You can use it as much as you can. And by the way, run relational databases if you can afford it, because it's very a corner piece of stability in production. And you can see also that we added the foreign key, so we can see that our team ID is always a real thing and not something the user hacked in. And yeah. So one thing to do with your favorite programming language, every language has something called assert. Yes. Yes. There were like hand raised.
No,
there was a message in the chat.
Yeah.
I cannot switch to the chat yet, but I can finish the presentation 5 minutes, and I think it's okay.
No worry. It was just a joke. I'm just was writing Cher and Madonna and Prince can't join because they need to have first name and last name.
Okay. Nice one. Like as I said, like every programming language has something called assert. Even though you have no types, you have no like formal declaration to have, there is always assert. So one advice I can show you is like just use assertion as much as you can when you validate data. It doesn't cost you a lot, and the runtime cost is not that high. And failing hard and loudly and quickly when you input data that is faulty in the system is much less burden than having wrong data in databases, or some very tricky part of the query you want to solve for the client, which is not right, and so on. So let's go over quick use cases of this kind of programming, and this is extremely successful in programming world actually, and most of the world are even not aware of it. For instance, SQL is purely declarative. You just have to declare what you want, and the database will figure out how to get it for you. So you don't have control, you don't have state. You can still optimize queries, have different approach, and so on. It's not like a zero effort thing, but SQL is a very powerful tool and very well supported, and databases are amazingly performant in the modern hardware. So why not using it actually? Actually, Kubernetes, one of the most revolutionary piece of software in the last decades, is totally declarative. Normally, when you are not using like help, like Helm templating, Helm escape stuff, normally you declare your manifest, you give it to the Kubernetes cluster, and it try to reach the state you state in the manifest. And that's the core engine of Kubernetes, and that's why it's so powerful, because even though your deployments are very complex, you manage to describe it well. The cluster will solve it for you. And last but not least, we've seen a lot of, because we are in crypto actually in Ledger, so we have seen a lot of scams and abuse of users, right? Because most of the blockchain operation and the blockchain logic is executed in something which is called a smart contract. And the thing is, Solidity, the language that is mostly used to write what's called smart contracts, is very imperative and very object-oriented, and so you have tons of state issue. You have tons of bugs that needs to be proven, analyzed, and then corrected. Correcting things on the blockchain is not an easy task to do, because things are kind of immutable. So maybe the solution to this kind of scams and rug pulls and every thing we can think of as a shady crypto stuff is to have a more declarative language using smart contracts and more like declarative primitive to interact with like this kind of databases which are blockchains. But it can be the subject for another talk. So thanks for your attention. I hope you liked it, and let's go for questions.
For all the things that you have said, is it or is there some tooling or good practices to have to use it as a team to make it perfectly clear for all the team, because it should be complicated?
Okay, so a lot of the things are linked to the programming language you use. So my first advice will be to use to have clear like guidance and a clear team policy on how you want to code. And not everything is enforceable using a compiler or using a static analyzer and such, but I think these are the key to have a scalable software, is to have either, if your language is dynamic and you don't want to put on your team the burden of having types to specify static analysis, good code reviews, good team culture. Don't hesitate to write documentation on how the code should run. And I think it's much of having a declarative mindset and like, let's write interfaces at query and interpreter instead of just having imperative ordering of code. And depending on your issue, sometimes most of the time it's overkill, but usually for tricky business logic issues, it's something you can always stand in. It widely depends on what you use. If you use, for instance, in the JS ecosystem, you have TypeScript. So, like, types are just very powerful unit tests if you think of it hard enough. You should start to use types more and more, and to leverage to the maximum extent what your compiler is able to prove. Then you can have a much more safer environment to program in.
And we had a question from Stefan as well.
Mm-hmm.
Yeah, sorry. You mentioned we have assert in SQL and in many languages. Do you think we should use both of them, or we can rely on the database only, or the earlier is better, like the programming language, because we can use assert before even querying the database?
What I can say about this is like, when you are studying military strategy, there is something called defense in depth. Like you have several lines of defenses that are maybe not perfect, but combined together, they're much, much more stronger. I think having like the database normally is the backbone of your your whole company, if you think about it. So having the more check on it is the better in terms of data quality. And instead, I doesn't want it to be too Postgres focused, but in Postgres you have something called domains, which are actually quite awesome. You can define custom types with constraint attached to them and reuse it in your schema, so you have something consistent. And there is maybe another talk to do about safety and Postgres, because it's a very wide topic. Yeah, basically you need to do both, because sometimes you want to where you want to do asserts. It's like when data enter your system, so in your database or on tables when you insert data, and in your API is just fail as soon as possible. And actually validate data, try to have a nice validation error for the clients, okay, but make sure that at the earliest time possible you validate the data is correct. And so
in such case, we don't need the data validation in the database, because if we use our own API to put data, like an API, I'm a backend engineer, so I mostly create APIs. And if we use an API to put some data in the database, no matter what the database itself, maybe we don't need to rely on the database itself, and we don't care about the data quality in the database because we already validate the data before.
I think it doesn't cost that much to put constraints in the database, actually. And so I tend to do both, actually. Because, for instance, I'm also a backend engineer. Data comes in the API. You need to validate it, because sometimes you are doing codes which are just manipulating domain data and sometimes interacting with the database. So if you shuffle the assertion in the type constructor, I'm not saying about asserting in every query. It's imagine you have a transaction ID that needs to be positive. Sometimes you want to get it from the API, assert that this is positive. So once you create a new transaction ID, you assert, and it depends on your programming language and how you handle errors. But asserting is is a basis. If you want to have more fine-grained error tuning, it's better, but it's another topic. You assess that every time you have a transaction ID in your business code, it has already been checked by your basically your domain model. And then it doesn't cost a lot to add also the check in the database, because who knows, the APIs comes and goes, but the data is staying, sometimes the database is staying the same. So it is very worth it to have it, I think, several times. And actually, if you think about it, a third time in the front end before they are sending data. So your line of defense. Between
but I'm a front-end engineer, so that's why I'm only speaking for myself.
There is a very nice sentence in cryptography and security engineering. It says, don't trust, verify. So really, don't trust, verify. Even though your API are lawful and so on and so on, no, you verify it before it reaches the databases, because once it is in the database, normally it says guarantee of storage that are much higher than the other systems.
Yeah. Okay. Thanks.
Well, thank you very much for this very comprehensive and dense yet very useful talk. I'm very happy we'll have a replay to get back to, especially to get back to some specific points. A takeaway I got from this is that to choose the right tools in a large system, one of the key criteria is how specialized it is for the task at hand in order to reduce the complexity. Is that a right understanding?
Yeah, for instance, sometimes you are using ORM. I won't get into the whole debate, but if you use SQL was engineered over dozens of years to answer business queries on data. So usually you have much less bugs and much less query performance issues, which are kind of bugs if you squint hard enough when you are using raw SQL. So maybe the goal is to find a library which allow you the freedom of having your own SQL to have a proper DSL for your use cases, and don't have put too much burden into crafting the right queries. But it's very tricky equilibrium to have. But yeah, the key takeaway is like, if you have tools that are doing the job, use the tools. And yeah.
Well, thank you so much. Is there any other question? Seems to be good. Well, thank you so much. Oh, yeah, Alex.
Yeah, I have an open question. So in the solution you mentioned, there is a three paradigms. So functional, decorative, and object programming. And with now the emergence of intelligence artificial, do you think there will be another paradigm, a fourth one?
First of all, I cannot predict what are the paradigm. What future paradigm will be actually and they are. I don't see them as exclusive. It's just tools overlapping. What the feedback I have for early contribution using IA on our different code base and feedback from developers in our teams are like, it's a very like productive but dumb intern to work with, and for some languages it works very well. For instance, for Go, for Python, for JS, it works amazingly well. Once your languages is already very declarative, like what you are doing with, for instance, ChatGPT or AI tool, is like you are telling the AI what you want and what is your intent, for instance, with Copilot, and it tries to complete it. And yeah, if there is a lot of boilerplates, it will work very well. If there is no boilerplate because you have the right abstractions, then it's kind of limited. Like ChatGPT is very bad at designing database queries that are good, because they're just translating the English into SQL, not leveraging the knowledge of SQL to answer the query.
Okay, thank you.
So maybe it will trigger a change in what we think about programming, that all this time we could have specified what we want, and now we have the tools to do it. So maybe it's at the programming language level we need to evolve and to provide more better solutions that's using a lot of boilerplates.
Okay, thanks.
There a question from Stefan, I guess? I've seen a hand.
Yeah. On these specific topics about AI and the new paradigm, I think I have a really small answer. Is AI will not change things, because product owner already tried to explain to developer. So we was the AI before, so we're just trying to explain again. But the next paradigm can be with quantum computing, because it's completely changed the way we think computer. And in that case, we will have more than object-oriented or stuff like that, because we can apply object-oriented, like with state or stateless, with quantum computing, because it's stateless by default, because you have all the result at the end, because you only put your cursor when you stop, when you ask. So, yeah.
It's a good thing to go with quantum programming, but for me, I see it like another type of device. You know, you have GPUs that can do a lot of computation in parallel. For me, like quantum computers are another kind of GPUs. They are solving very focused and narrow problems with dedicated hardware.
Yeah, I'm not sure of that, because they already implement some existing algorithm, like sorting algorithm, or adding, dividing, multiplicating algorithm into quantum computing. So yeah, and the result is not the same, because you can't get the right answer of your question with a quantum computer, because you always get the two answer at the end. It will be yes and no at the same time. So it's, I think, a different tools. So that may why we have a next version of oriented programming, functional programming, or because we have much more than the three you mentioned. We have also matrix programming. I learned that on Wikipedia, which is completely a mess.
Array programming is a very niche tool. It's very powerful.
Yeah. So
APL stuff is crazy.
Yeah, but the problem will be when they put AI on quantum computer, because the power of quantum computer is really much more powerful than our current computer. So when we reach this point, I think, yeah, it will, Terminator will come too. So it will already too late. Sorry,
Well,
Alex.
waiting for the rise of Skynet, we've left with a lot of things to think about then. Thank you again, Valentin and Paul, for setting this up and for your time. And we were very happy to welcome you guys today. So thank you so much. Happy to do anything else with Ledger at some point in one way or another. Thank you everyone who joined in, who contributed to this talk and the different very interesting and passionate questions. Yeah, enjoy lunch for some of you, a good evening for the other, and see you soon, I guess.